Yes, Brian said, I'm Rob Fleury from Arup in Sydney, Australia. This is my work on evaluating different thermal radiation models, co-authored by Michael Spearpoint and Charles Fleischmann, both of the University of Canterbury in New Zealand. So this is some research that I carried out during my study at the University of Canterbury. Just to provide a bit of context and motivation to the research. It's part of a joint project between the University of Canterbury and BRANZ, being Building Research Association of New Zealand, and funded by the Foundation of Research, Science and Technology, so I must acknowledge their support. Basically, there's a existing zone model called BRANZ Fire, used throughout New Zealand and wider, and it's currently being upgraded to include risk-based modelling, so creating a quantitative risk assessment tool. Basically, it's going to use Monte Carlo sampling to address inherent uncertainty in design fires by populating rooms with sort of randomly populating rooms with furniture and other items based on the likely scenarios. For example, a lounge living room might have one or two sofas, bookcase, things like that. So create a range of design fires which will then translate to a range of outputs, giving the user sort of an overview of the probability distributions of what we're likely to see as the outputs, because it's never going to be just one given answer. Obviously noting the limitations that a zone model has. One aspect of the new BRANZ fire model will include a radiation and ignition submodel, which is what this work is about. So the aim of my research was to look at existing and new thermal radiation models so that they can then be implemented into the new BRANZ fire model. So this essentially, you take the initial fire, and the radiation and ignition submodel helps determine if or when secondary objects within that compartment will ignite due to thermal radiation. There are three aspects to the submodel. Firstly, direct radiation from the flames. Secondly, the sort of radiation exchange within the compartment. And thirdly, actually ignition of the secondary objects. The scope of my work was purely dealing with the first aspect, so just direct radiation from the flames, with the other work being carried out by Greg Baker of BRANZ. The approach for my work had two components. Firstly, an experimental section, which I will go into in a minute, whereby measurements of radiant heat flux were taken around a propane gas burner, and then comparing that experimental data with what the theoretical models predicted under the same conditions, same fire conditions. So I looked at 6 different radiation models. Firstly, the first one there is a simple correlation based on experimental data. Secondly, a spherical model known as the point source model, which is depicted here. Essentially, that assumes that all energy from the fire emanates from a single point source, which is located in the center of the fire, and energy radiates sort of radially outwards from that point source. I then looked at 3 cylindrical models. One of them is sort of depicted here, where the fire is assumed to be a cylinder and radiation emanates from the surfaces of the cylinder. And then finally, I attempted to come up with a sort of original model based loosely on some other existing models, whereby the fire was assumed to be 2 perpendicular intersecting planes, and then targets could be moved sort of relative to those planes. And so that was sort of an orientation-specific model. Looking into the experimental section, the experiments were performed at the University of Canterbury in their furniture calorimeter there. This is sort of a schematic of the lab, the gas burner in the centre. Then I mounted 8 heat flux gauges on 2 trolleys, so 4 on each trolley. This represents a trolley. You can see here in the photo, that's the trolley there. And the trolleys could be moved in and out relative to the fire. The gauges are at 4 different heights relative to the base of the flame. and the gauges could also be moved radially across the face of the flame. The burner, as I mentioned before, used propane gas, and the reason I used a gas burner as opposed to furniture items or other fuel sources was essentially just to have a reasonably constant and repeatable fire source on which I could kind of compare all my measurements with. I used 3 different burners of different geometries, which was kind of to represent different furniture items. So I used a square burner, we can see there, and then a slightly rectangular burner, and then a more rectangular burner. So 3 different aspect ratios of 1:1 through to 3:1. Just to give you an idea, that burner there is roughly 1 foot by 1 foot. The intent of the experimental program was basically to come up with quite a wide range of experimental data to kind of test the limits of the different radiation models, see where they might fall down, where they perform strongly, and have a good basis for comparison. One important input into most of the radiation models is the flame height. So to determine this from the experiments, I use video imaging technique using a software called ImageStream. Essentially, I took a video of the fire at each heat release rate setting. What I failed to mention before was that I looked at a range of heat release rates between 100 and 300 kilowatts, and the upper limit was essentially bound by the geometry of the lab. If I went to heat release rates too much higher than that, then the flame was extending up into the hood. I could no longer video the flame, and it wasn't really I couldn't get realistic measurements because some of it was shielded. So I took video of each heat release rate and then broke the video down into individual frames, averaged those frames over time, and then used the software to come up with this contour intensity plot, which shows where the flame existed during the sort of the period of the video at different probabilities. So I could take the 0.5 contour, which is roughly in the middle here, determine the height of that, and that gives me the mean flame height from the experiments. When I compare that to the Heskestad and Thomas correlations for flame height, I saw that the image stream or the video analysed flame heights are actually lower than what those 2 correlations estimated under the same fire conditions. So the same heat release rate, the same diameter, the actual experimental flame height was lower. So I find that quite interesting, and I feel that this could have been there could have been opportunities to explore this in a little bit more detail. However, it was kind of going outside of the scope of my work, so I sort of just left it at that. These plots compare the measured heat flux along the horizontal axis with the predicted heat flux on the vertical for each of the 6 different models. What we can see is that there is quite a range of sort of accuracies shown by the different models. So a very accurate model which predicts the heat flux quite well will have all of its data points close to the equality line. So just going briefly through the models, the first one is the simple correlation based on experimental data, and it has quite a wide scatter of data, so not overly accurate. The point source model was seen to be the most accurate model, so it had the best match to experimental data under the conditions tested in the experiments. This model here, one of the cylindrical models, seemed to sort of systematically over-predict the heat flux, and the other ones showed sort of an element of scatter, but still reasonably close to the equality line. So as I said before, the point source model was shown to have the most accurate predictions, which was somewhat surprising given the relative simplicity of this model in comparison to some of the others. This plot here shows the average percentage error of different models, when I say percentage error, I mean it's a absolute value, sort of just to show the closest of fit to the experimental data. So again, we see the point source model with a relatively low and consistent percentage error, where the different coloured bars represent the 3 different burners tested, so the rectangular and the through to the square burner. We see the point source model quite robust, quite consistent in dealing with the different geometries, whereas this model here, the simple correlation, really breaks down when we get out to the rectangular burners. These values summarise the average percentage errors for the different models. So we see the point source model had an average error of 29%. The next most accurate, the Dayan and Tian model, at 41%. We can see that this model here, with its over-prediction in the heat flux, I sort of looked into that in some detail and found that one of the components of that model was calculating the average emissive power of the flame, and that was based on a correlation which was taken from quite a few tests, but mainly on a much larger scale. So pool fires up to 10 metres in diameter, whereas my experimental program was on a much smaller scale. So I think that's where that model struggled, was just the sheer scale of the experiments. This table summarises the average percentage error for different target orientations. So first of all, we had the vertical heat flux gauges and then moved them to the horizontal position as well. Point source model was the most accurate for vertical targets at 18% percentage error on average, and for horizontal targets, none of the models performed particularly well, but the Dayan and Tian model was the best there. The simple correlation simply wasn't able to distinguish between vertical and horizontal targets, so I've left that result out. This sort of breaks down the results into different heat fluxes received. So these values arise from data taken that was sort of quite far from the burner or at very low burner heat release rates, and then greater than 10 sort of at higher values. Point source model was seen to be quite consistent across the different ranges, which was somewhat surprising because there is some advice which says that the point source model should only be used for heat fluxes less than 5 kilowatts per metre squared received. So it seemed to perform quite well there. It did become less accurate at higher heat fluxes, and I feel that sort of if we went to very high heat fluxes, it might sort of fall down even more. But overall, it was still quite consistent there. The gauges could be mounted sort of centrally along the burner axis or offset, so sort of just moved laterally, and all of the models seem to deal with that offset relatively well. Point source model, again, the most accurate there. There are some obvious limitations to the work. It is meant to represent single object fires within compartments, as that was sort of the scope of what Brandsfire is looking to model. The use of propane gas versus real objects that we would see in a burning compartment is obvious. Would have loved to go and burn 100 sofas in the lab, but it just wasn't really feasible. And the use of propane gas just gave me a consistent and repeatable fuel source from which I could take all my experimental data. As I mentioned before, the heat release rate, I sort of couldn't go much higher than 300 kilowatts without shielding the flame from the heat flux gauges. So that obviously our compartment fires that we would see in an unsprinkled compartment would be much higher than that. The effective diameter of the flames that I was using, sort of maximum 0.6 metres. Some of the models have been correlated against much larger fuel sources. However, on the scale of compartment fires, it's not too bad. It's sort of an order of magnitude it's within an order of magnitude of what we'd expect. And the input parameters for the models, I looked at sort of a range of literature to try and get the most appropriate input parameters for the fuel source used, and looked at the sensitivity of those input parameters. However, there may be scope to sort of further refine the exact values used and then applying the correct values to the given situation in an actual compartment fire. So in terms of selecting an appropriate model for use within Brands fire, the two main important factors are, first of all, accuracy, and we've seen that the point source model was deemed to be the most accurate model, and secondly the Dayan and Tian model, which is one of the cylindrical models. The second important factor is how easy is this to implement into a computer model, and how easy is it for the user to actually use it? How many inputs does the user have to input into the model? So just quickly looking at the sort of the overall equations on which the two models are based. Point source model, relatively few inputs, and inputs that will be that the model already requires anyway. So things like the heat release rate of the fire and the sort of the radius of the fuel source. So we already know those things. Therefore, point source model quite easy to implement into Brands fire. On the other hand, this cylindrical model requires these configuration factors to be determined, and those have a much higher requirement for inputs, such as the specific dimensions of the fuel source and orientations of different targets. It's just much more difficult to implement into the model. So in conclusion, the point source and the Dayan and Tian models provided the best match to the experimental data that I took. Point source model, surprisingly, was the most robust and seemed to deal with different situations relatively well. And therefore, the point source model has been selected to be implemented into Brands fire for the radiation and ignition submodel to be input into the quantitative risk assessment tool in the forthcoming version. Thank you.
Thanks. Do we have questions? Kevin?
One thing you might look at is when you use these cylindrical models and you have to choose this emissive power. I mean, notice there's a fourth power dependence on that T sub F.
Yes.
So you can get numbers all over the map.
That's right.
If you were to choose your T sub F so that the radiative output from your cylinder, whose size would be roughly the same size of the fire, I can't imagine that the errors would be so large. Because you would essentially be distributing the same radiative energy over this cylinder as opposed to just a point.
That's right.
And as you get closer and closer, I would expect that the solid flame models, assuming it's got a consistent radiative output as the point source model, would give a better result.
Right. Only one of the cylindrical models actually used the flame temperature as an input. The other ones were based on correlations for the emissive power of the flame, which were independent of temperature. It was just that Dayan and Tian model. That
the emissive power of the flame. I mean, again, if you choose the emissive power of the flame such that when you integrate over the surface area of your cylinder, and assuming your cylinder has the same height roughly as your fire, I would guess that you'd be closer to matching the experimental data. Rather than just choosing an emissive power, set your emissive power such that your cylinder and your point source radiate the same amount of energy. That's all I'm suggesting.
Okay. Yeah, that's a good way of looking at it. Yeah.
Any other questions, comments? All right, thanks again, Rob.
Mm-hmm.